Now let's talk a little bit about other ISAs, other instruction set architectures. We spent a long time talking about MIPS, so I'd like to give you some feeling for what the parameters are that other computers use. So here are some other ISAs that you could talk about. x86 is the standard that Intel and AMD use, and it's what you find in most desktop and laptops. ARM is provided by ARM, but there are lots of manufacturers of ARM devices, and it's the standard embedded ISA. So you'll find it in cell phones, tablets, printers, and the like. Java has a JVM, or a Java Virtual Machine, which uses its own bytecode ISA. PowerPC is another popular ISA that's used in a lot of embedded devices. Your car probably has a PowerPC processor in it, for example. Spark used to be a very popular ISA and is still reasonably popular. It's made by Oracle and a bunch of other companies these days. NVIDIA has an ISA called PTX for their GPUs. And of course, there are a whole bunch of these. Everything from digital signal processors down to teeny little microcontrollers all have their own ISAs. So now we're going to take a look at a few issues across ISAs and try and compare them. The point of this is to give you a feeling for the choices that you can make when you're designing an ISA and get a feeling for why MIPS may or may not be a good choice. So we're going to look at different types of machines, classes of ISAs, addressing modes, issues of instruction width, and we're going to finish up with a discussion of CISC versus RISC. So what sort of basic machine types do we have? Well, there are two main types that we can talk about. One is a memory-to-memory machine, and the other is one that has architectural registers. So a memory-to-memory machine can directly manipulate memory. Here's an example. You could say memory of address 0 equals memory of address 1 plus memory of address 2. It will go through and load the correct memory, do the operation, and do the correct store. There's some problems with this. If you have an operation which needs temporary values, you have to store those temporary values in memory. So if remember the function that we've been looking at, this f equals g of h and ij. This has a lot of temporary values, and now you're going to have to store and load them from memory. This is a real issue because memory is slow. It takes a long time to access data from memory, and memory is also big. So for each one of those accesses, we're going to need 32 bits of address to identify it. So it's going to take a lot of code. Architectural registers, however, make it easy to hold temporary variables. We've seen this in MIPS. We have 32 registers that we can use for holding temporary variables. Because register files are so much smaller, only 32 entries, they're much faster to access, which means our programs can run faster. And we need fewer addresses in code. So we saw that we only need 5 bits to index into our 32-bit entry register file, as opposed to having a whole memory address, which is 32 bits. But of course, it's never that simple. Memory-to-memory machines are one extreme, architectural registers are another extreme, but we end up with something in between. x86 processors have a few registers, but they also support memory-to-memory operations. ARM has a whole bunch of really complicated addressing modes that make architectural registers somewhat harder to use. And of course, on any machine, if you run out of registers, you have to spill your data into memory, so you end up using memory transfers anyways. So now let's talk about some ISA classes. These are different types of ISAs that have been developed over the years. So the simplest one is an accumulator. An accumulator is an architecture that has one register, and this was a very popular architecture when computers were very hard to build. Because for an accumulator, you only needed to build one register, and this was the accumulator. It also makes it very easy to write code because all instructions automatically go into the accumulator, so you don't need to add a lot of information. So add A is going to say, go get the memory at address A and add it, and well, there's only one register, so it has to be added to the accumulator. General purpose register files, the load store architecture, this is what we've seen in MIPS. You generally have 2 or 3 addresses for whether you're doing things with 2 register files, writing to a register file, or you're loading a memory address. There are also more sort of a hybrid of these, the general purpose register file with register memory, and this is what x86 supports. So here you can have 2 addresses. So we have add RAB, and this is going to go to memory, load B, and add it to RA. And then we have a stack. A stack is not a register file, but it's sort of like the stack that we saw in memory. Everything gets stored on the stack, and then you can operate on what's on the stack. So here you don't need any addresses. If you do add, it's going to take the top of the stack, and it's going to add it to the thing below it and store it on the top of the stack. So how do we compare these different approaches? So these are all very different. Do you compare them in terms of how many bytes you need per each instruction? Obviously, if I don't have any registers to specify, like in a stack, My instructions are going to be much shorter. But do I compare them in terms of number of instructions? Maybe I need many more instructions for stack operations. Or how about cycles per instruction? Are some of these instructions much harder to do? We know that loading memory is much slower, so it's going to be more cycles per instruction. So let's compare some of these on some simple code. Here I'm going to do C equals A plus B. And if we look first at this stack, you see you have very small instructions, but you need a lot of them. And that's because each of these instructions only specifies one thing, which is going to be pushed onto the stack. If we look at the accumulator approach, it's pretty good, unless you need temporaries. Because the accumulator only has one register, any temporaries have to be stored to memory. The register memory approach has very small code. It's very easy to write code here, but it's hard to build in hardware. Because now when we have instructions that add things to memory locations, we have to go get the data from the memory and do the add. And if we compare it to the standard register load store, this is what MIPS has, we see we have lots and lots of simple instructions. And you can see down here at the bottom examples of what sort of processors these are. So accumulator is a much older style processor. It's still used a lot in the 8051 microcontroller, but not on any major machines. Register to memory is x86, and everything else these days is pretty much register. So now let's talk a little about addressing modes. So not all of the ones you see here are in MIPS, and in fact these are the ones that are in MIPS. So MIPS has 4 addressing modes. You can either get data directly from a register, you can get data from an immediate, you can get data from a memory location with an offset, or you can get it directly from the memory location. And we've seen all of these ways of accessing data in MIPS. Here are some other complicated ones. We have auto-increment, auto-decrement, and scaled. And these both access data and then update the register. Take a look at scaled. It's doing something really complicated here. It's adding a constant to one register, to another register, and it's multiplying that third register by some offset. This is a really complicated memory access. So why would you want all this stuff, these auto-increment, auto-decrement, and scaled? Where would this be useful to have? Well, think about if you're going through an array. Say I have a large array of data, and I want to increment every 4th element. I know that my code is going to go load data and then add 4 to the address every single time. If I have an auto-increment or an auto-decrement memory access, then I can save having to have that extra instruction to add or subtract from my memory address. So another issue with ISAs is instruction widths. That's the number of bits per instruction. And as you know, MIPS has 32 bits in every instruction, but that's not the only choice. In general, they're variable width and fixed width ISAs. So variable widths obviously has different widths for different instructions. This is both good and bad. So if you look at x86 from Intel or AMD, you can have between 2 and 6 bytes for an add instruction and between 2 and 4 bytes for a load instruction. This means you can make very compact code. If you can specify an add and a load with only 2 bytes each, you can use half as much space as MIPS. But it makes the hardware very hard to build, because the hardware can't load 4 bytes and know it has the next instruction. It has to load somewhere between 2 and 6 bytes, and it could get somewhere between 1 and 3 instructions out of that. So it makes it much more complicated to build the hardware. Fixed width obviously has the same width for every instruction. We've seen this in MIPS, where there's 4 bytes for an add and 4 bytes for a load. And this makes for larger code. You can't have shorter instructions than 4 bytes, but it makes it much easier for the hardware. The hardware always knows that every 4 bytes are a new instruction. And of course, to make things complicated, you can also have multiple widths. So ARM and MIPS both support 32-bit and 16-bit instructions. And the reason they do this is so that they can reduce code size. So if you're building a printer and you want to put an ARM or MIPS processor in there, and you can make your code half as big by using this reduced width, you can then save money on how much storage space you need in your printer. So today, general purpose register machines dominate. Literally all machines today are built using registers, like we saw in MIPS. There are major advantages to this. The registers are much, much faster than memory, makes your code run faster. You can hold temporary variables. This makes it much easier to write things like that f equals g plus h minus I plus j that we saw earlier. And it's much easier for compilers to use. The instructions are regular and they have uniform use of resources. So they all use the same registers and they work in the same way, which makes it much easier for a compiler to think about things. And this gives you improved code density. You don't have to have as many addresses if you need to specify data directly in memory, and this is why registers are better, because you have only 5 bits, for example in MIPS, to specify a register, as opposed to needing 32 bits to specify an address in a memory machine. So I just told you that all processors today use general purpose registers, but we spent a while talking about how x86 is a memory to register architecture. So what's going on here? Am I tricking you in some way?